This is the key to test 6. We have a satellite is in an elliptic orbit about a planet, about a mass M planet right here. And denoting by R0 and R1, these quantities right here, respectively, the minimum and maximum values of the distance from the satellite to the center of the planet. We want us to derive this relationship right here. And we're to start with this equation right here that's given to you. So H is the angular momentum per unit mass of the satellite. So further show that the radius of the curvature at A and B is given by this equation right here. So we're going to start off then with, this is a starting point equation, 1 over R equals GM over H squared plus C cosine theta. And this is set up for a situation for theta equals 0. You're going to be located at point A, and we'll look at moving around like so. So A is going to be measured, or theta is going to be measured counterclockwise, starting from right there in the figure. Okay. So what we're going to do is we're going to look at it when R is equal to R0. Right there, we have GM over H squared plus C times the cosine of 0 degrees, which is 1. And then when R is equal to R1, which is over here, and then you have it equal to GM over H squared, again for this equation right here, plus C cosine theta, but it's cosine of 180 degrees, which is a -1. So you end up with this. Now, it's very easy to see that if I add these two equations together, I'll drop off the C's right there. So I'll have 1 over R0 plus 1 over R1 equal to this side added together, or these sides right here, right-hand sides added together. And I get 2 GM over H squared then. Now, we're going to look at the, trying to do the second part of the problem, which is to show that the radius of curvature at these points A and B is equal to this right here. So if we do a free body diagram at A, we have F right there acting to the right, and it's the universal gravitational force. And we call it the X direction. It doesn't really matter, but somebody's force is the X equal to M times A sub X, and so you have that. And the value of the force is GMM over R0 squared, and that's got to be equal to M times the acceleration in this direction right here. And the acceleration in that direction is given by the velocity at A squared divided by the radius of curvature. Okay, so if you take a look at this equation right here, we can create a 1 over rho term by putting the M and the VA squared to the other side. So you end up with GM. This little m is going to cancel out with that little m. So you end up with GM R0 squared, and the VA squared will come over with it to become VA squared. Well, R0 squared VA squared is H squared. And so you have 1 over rho equal GM over H squared. Well, if you take a look at this, GM over H squared is 1/2 of that right there. So there's the solution. And it doesn't matter whether you chose to do this at A or B, you'll still end up with that as the solution. So